Any questions about the homework or anything? All right, the next topic, and the last topic before we start talking about mass and force and stuff like that, is circular motion. There's some really useful stuff that we can say about objects when they're moving in a circle. We're going to break this up into two types, break it up into two categories. The first one is called uniform circular motion. And the second one is non-uniform circular motion. That one's not very creative. So, I don't know, think about what an object can do when it's moving in a circle, and give me a guess or two about what those two categories stand for. Yep?
Uniform is when the acceleration is constant speed.
Constant speed, yeah. So one thing, that's right. So uniform circular motion means constant speed. And non-uniform circular motion means, changing speed. As far as the acceleration, a big part of what we're going to talk about with circular motion is the weird stuff that happens with acceleration because, as we've been talking about, acceleration is a change in speed or a change in direction, and something moving in a circle is changing direction all the time. So here's what we're going to start with. Velocity and acceleration can seem complicated in circular motion. But it makes a lot of sense if you think about it the way that we've been thinking about objects changing speed and changing directions intuitively. So it makes sense if you think about it in terms of the velocity direction the acceleration parallel to the velocity, and the acceleration perpendicular to the velocity. And then, the acceleration, the total acceleration is equal to the parallel part plus the perpendicular part. So let's start by just thinking intuitively about these directions. Ooh, that's a good circle. So this is the center. Let's say that an object is moving counterclockwise around the circle. And let's call these points A, B, C, and D. And let's think about three cases. No speed change, speeding up, and exploding. No. Let's do slowing down instead. Okay. Okay, so no speed change. Well, all of these we're going to do the same thing. You're going to think about the velocity direction, the acceleration parallel to the velocity, the direction of the acceleration perpendicular to the velocity, and the total acceleration direction, what you can figure out. These you're going to do the same thing. Okay. So choose your groups and go draw these vectors on the board the same way that we've done with cars moving around turns and balls rolling up paths and stuff like that. Okay, so what's the one thing that is the same in all of these cases?
Velocity.
Well, velocity is the same. Okay, so there's two things the same.
Perpendicular acceleration.
Yeah. So two things are the same in all three cases. The first one is that the velocity, that always, so the velocity vector is always tangent to the circle. In the direction of motion. And the second thing is whether the object is speeding up or slowing down or moving with a constant speed, there's always a perpendicular part of the acceleration pointing towards the center of the circle. Okay? You can think of this as the thing that makes motion circular. This is what causes or defines circular motion. Since in circular motion, that perpendicular part always points towards the center of the circle, we're going to call that centripetal acceleration. That's a fancy word for toward the center. The thing that changes depending on what kind of circular motion you have is what happens with the parallel part of the acceleration. So the parallel part of the acceleration changes for different types of circular motion. And this, well, you could always call the parallel. So the velocity vector in any kind of motion is always tangent to the path. That doesn't change here. The velocity vector is tangent to the circle when something's moving in a circle. And so the parallel part of the acceleration is also tangent. And so in circular motion, people call that parallel part of the acceleration the tangential acceleration. And the tangential acceleration is only non-zero for, is it non-zero for uniform circular motion or non-uniform circular motion? Yeah, I said that as sort of a double negative, but if it's uniform circular motion and the speed isn't changing, you don't get a tangential acceleration. If it's non-uniform and the speed is changing, then you do get a tangential acceleration. And in every case of circular motion, the acceleration is equal to the tangential acceleration. Let me do it in the other order. The centripetal acceleration plus the tangential acceleration. Okay. That's no different than any other kind of motion. We've always broken up the acceleration into a parallel part and a perpendicular part. Now we're just calling them different things. So you already understand where the direction of the acceleration comes from in circular motion, but we don't know the magnitudes of those parts. We can calculate those, though, and in order to do that, we have to define 3 new kinematic quantities. So to calculate the magnitudes of the velocity vector, the centripetal acceleration vector, and the tangential acceleration, we need to define the angular position, angular velocity, and angular acceleration. Okay, so the angular position I'm going to denote that as theta. And you can define that if that's your circle and your object is moving around this circular path. So let's say this is the object at some instant. Draw a line between the center and the object. And that angle theta, the angular position, is the counterclockwise angle from the positive x-axis to that line. So theta is the counterclockwise angle from the positive x-axis to the line between the center and the object. Bless you. When you're going, just like when you're talking about cosine and sine of angles, if this object was over here in the 4th quadrant, you could talk about that as an angle of positive 300 degrees or whatever. Or just as well, you could talk about that as an angle of negative 30 degrees or whatever. So clockwise is negative. The units of angular position well, this has to be given as an angle, and we're going to express it in radians. Notice that theta changes as the object moves. And so you could represent theta as a function of time. And if you have theta expressed as a function of time, you can take time derivatives of it, and that's how we're going to come up with the definition of the angular velocity and the angular acceleration. They're just going to be time derivatives of the angular position. Okay, so angular velocity we're going to represent that as a lowercase omega, like a round W. Angular velocity as a function of time is equal to the time derivative of the angular position. That's, you can think of that as the definition. The units of angular velocity are radians per time, and so the SI units, the units that we're going to be using, are radians per second. The sine of omega tells you the instantaneous direction of motion. So if omega is positive, the object is moving counterclockwise around the circle. And if omega is negative, the object's moving clockwise at that instant. Okay, so based on this definition of those signs, let's think for a second about so first, let's say that there's the circle, the object's up here, okay? Let's say that the angular velocity is positive. What's the direction of the velocity vector? Yep. That's right, because omega positive means that it's moving counterclockwise, and so the velocity has to be this way. Okay. So there has to be that connection between the direction of, the sine of omega, the sine of the angular velocity, and the direction of the velocity vector. Okay, and now let's say that we're looking at this point, and let's say that omega is negative. What's the direction of the velocity vector? So down, right. So in this case, omega negative means it's moving clockwise, and so the velocity vector has to be that way. Okay. If you know the direction of either one of those, the velocity or the angular velocity, you can figure out the direction of the other one. Okay. Then the last quantity is the angular acceleration. How do you want to define that? If you were inventing this, how would you define this? Yeah, exactly. So this is the angular acceleration as a function of time is the time derivative of the angular velocity. And the second time derivative of the angular position. The units for angular acceleration. No matter what system of units you're using, they're going to be radians per time squared. And in SI units, they're radians per second squared. And one important thing to notice, and this is similar to the same as how it works with one-dimensional motion with velocity and acceleration. If the object is speeding up, what do you think you know about the signs of omega and alpha? Yep. If the object's speeding up, the angular velocity and the angular acceleration have the same sign. And if the object's slowing down, they have opposite signs. Okay, so now we can use the angular position, the angular velocity, and the angular acceleration to give expressions for the magnitudes of the velocity vector, the centripetal acceleration vector, and the tangential acceleration vector. Okay, so that's what we're going to do now that we've defined these three things. So first is velocity. The velocity vector is equal to r times omega, and the direction is tangent to the circle in the direction of motion. This is the radius of the circle. So let's say, so this is the center. Let's call this point A and this point B. And let's say omega is equal to negative 20 radians per second. And the radius of this circle is 0.1 meters. Then first, what's the velocity vector at A? And second, what's the velocity vector at B? at A, so omega is negative 20, which means it's moving clockwise. Okay. So the direction of the velocity vector is this way. The magnitude is 20. Let's see. So the velocity vector is 20 times 0.1 in this direction. Any questions about that? Okay, and then, so if you want to express this velocity vector in components, how would you do that based on this information? Well, so we know that the direction is in the positive y direction, right? And so this is equal to, this comes out to 2 meters per second. So this velocity is 2 meters per second. Okay? Or you could write this as 2 meters per second in the j direction. Any questions about that?
Can you scroll up so I
Yeah.
can write something?
Yes. Just to there, is that right?
A little more. The velocity. Thank you.
Yep. So I guess I didn't write this originally, but you could think of this as an absolute value since you're just calculating that magnitude. So omega, whether it's, in our example, it was minus 20, but we just used the 20. Okay, so for part B, what's the direction of the velocity vector at B? Down. The velocity vector is, these haven't changed, so we still have 20 radians per second times a radius of 0.1, but the direction now is this way. So what do you get for components on this one? It's in the negative y direction, so you can think of that as 2 meters per second times that direction is 0, negative 2. You could also think of that as, if you ever get confused about getting these in components, remember that you can always just calculate the counterclockwise angle from the positive x-axis to the vector, and then just take the length times the cosine of that angle and the length times the sine of this angle. So what's the angle in this case? 270. So this would be 2 times cosine of 270, sine of 270. Cosine of 270 and sine of 270 is 0, negative 1, so you get this. And you could also write this as negative 2 meters per second times j. Yep.
How did you get 270? Isn't that 20? I'm
20?
confused by the...
Oh, I'm talking about, so we've figured out the, we used the formula to figure out the magnitude of the velocity vector, and we used our intuition to come up with the direction. And now to put that direction into, to combine the magnitude and direction into components, we we take the counterclockwise angle from the positive x-axis to the vector.
But didn't you have radian W omega at negative 2080 instead of positive 2080?
Yes, I didn't write that at first, but so this is how you always see it, but you probably want to think of that as an absolute value. Any negatives are just directions, so we'll deal with those negatives when we're figuring out the directions. We won't deal with them as calculating the magnitude of the vector. Does that make sense? Okay. Yep.
How you got 2 meters per second from 20 times like sine of 0.1 or cosine squared of 0.1?
Okay. Yeah, there's a lot of angles floating around, and it's getting confusing. So we broke up calculating this velocity vector into 2 pieces. Using this formula to calculate the magnitude of the vector, and using our intuition, that thinking about it in terms of a tangent and knowing that the velocity is tangent to the circle, we use that to come up with the direction for the vector. So we came up with, for A, we came up with the fact that we have a magnitude of 2 meters per second, and the direction is up in the positive y direction. Then all you're doing is, after that, you're using cosine and sine to figure out
So the 20 and 0.1 is just to get
the magnitude of the vector.
Okay.
Yep, because remember, any vector you can think of as, like any random vector you can think of as the magnitude of the vector L times the cosine of some angle, and let me call that phi, sine of phi. So that's just, you're just going to use this to combine what you know about the magnitude and the direction to get components. To get vector components. One thing that's going to come up a lot with circular motion, or one of the reasons that circular motion is such an important thing in physics and engineering, is, so notice, this is kind of a key idea. Any motion of a rigid body, anytime a rigid body is rotating about a hinge or some kind of joint, every point on the rigid body is moving in circular motion about that hinge. So every point on a rigid body moves in circular motion about a hinge. So these circular motion problems a lot of times come naturally from motions of rigid bodies, where you're trying to figure out the velocity and the acceleration of some point on a rigid body. So let me give you an example to work on. So let's say you can think of this as a real person golfing, or you can think of it as one of those golf club testing devices. But think of this as like a rigid body that's made up of a swinging arm and a golf club. You can think of this as the arms, and this is the axis of rotation. And the golf ball's here. This rigid body made up of the arms and the golf club is swinging this way at 35 radians per second. And let's say that the length of this rigid body is 1.7 meters. What's the velocity vector of the club when it hits the ball? And give it in vector components. So this circular motion it's a part of this circle, even though it doesn't actually complete the whole circle. The ball is down here. The motion is this way, and omega is 35 radians per second. The radius of the circle is 1.7. So the velocity vector points this way. The magnitude is 1.7 times 35, which is 59, what is it, 59.5 meters per second, pointing this direction. That's the positive x direction. And so that's 59.50 meters per second. Or you could also write this as 59.5 meters per second in the positive I direction. One other, so what did I say? Oh, so another thing that's important about about circular motion, besides the fact that it represents rigid body motion, is that a lot of times circular motion is a pretty natural companion to relative motion. So notice also, circular motion goes very naturally with relative motion. Because often motion is broken up into a circular motion of a point about the center, or a circular motion of an object around a center. and second, motion of the center. Okay, so here's an example of the kind of thing that comes up all the time. So let's say we have a wheel that's rolling to the left. The radius of the wheel is 0.3 meters. The angular velocity of the wheel, the magnitude of it, is 33.333, the threes keep going, radians per second. And the question is, first, what's the velocity vector at the bottom of the wheel, right at the point where it's touching the ground? Whoops. So what's the velocity at that point B? And second, what's the velocity vector at the top, this point T? Okay, you want to try to do that with relative motion? Yes. That's the spirit. Okay, so do it. You're thinking about this in the simplest order. So, okay, shut up. Okay, so if we want to calculate the velocity of B, the velocity of B relative to the ground is equal to the velocity of B relative to the center of the circle plus the velocity of the center of the circle relative to the ground. The velocity of B relative to the center, this is the circular motion part. So that's omega times r, which is 0.3 times 33 1/3, which is 10. And then the direction, you have to think about the direction. If it's rotating, so this wheel, in order for the wheel to be moving to the left, this has to be rotating counterclockwise. So the direction is this way. Okay? Does that make sense? So far it's a little, this can seem a little backwards. But so now you can represent this vector as, well, 10 going to the right. What's that in vector components? Yeah, 10, 0. The velocity of the center of the circle relative to the ground, what's that equal to? That's 10 meters per second going this way. So what's that in vector components? Yep, that's negative 10, 0. Does everyone follow that, the sign of that component? And so now you can add these two together, and you get that the velocity of the bottom relative to the ground is equal to 10, 0 plus, actually, let me change the order of these. So it's equal to negative 10, 0, plus 10, 0. And so the point that's in contact with the ground actually has no velocity at that instant. Seems sort of funny, but if you think about if it did have any velocity, it would be sliding compared to the ground. And if it's rolling, that's not happening. And so that sort of makes sense if you think about it that way. So it's weird that this wheel is moving, but at that instant, that point on the wheel has zero velocity. It's sort of a strange fact, but that's how it is. But that's not true of every point, so let's do the one on the top. So the velocity of the top relative to the ground is equal to the velocity of the top relative to the center plus the velocity of the center relative to the ground. This one still is the same. This is still negative 10, 0. The velocity of the top relative to the center is 33.333 times 0.3. So that's 10 meters per second. And let's see. It's rotating this way. So this velocity is to the left. And so what are the components of a vector that's 10 meters per second pointing to the left? Yep. Negative 10, 0. So now put these two together and you get the velocity of the top relative to the ground is equal to negative 10, 0 plus negative 10, 0 equals negative 20, 0 meters per second. Okay, so if a bicycle is going 10 meters per second that way, the point right at the bottom of the wheel at that instant has no velocity. The point right at the top of the wheel has twice the speed of the bicycle. It seems sort of funny, but that's how it is. And actually, there used to be a cool picture in the physics hallway of if you use the right exposure on a camera and take a picture of a bicycle wheel, you can see the spokes on the bottom of the wheel perfectly clearly. And the spokes at the top are blurry. And everything else is in between those two extremes because the top is moving really fast. The bottom is not moving. Okay, so any questions about that? All right, so now acceleration. We spent all that time talking about velocity. Now how about the centripetal acceleration? Again, just like velocity, we know from analyzing the velocity direction, the parallel part, the perpendicular part, we know the direction of this, we just need the magnitude. The centripetal acceleration is equal to omega squared times r, pointing toward the center, and And since you know that the speed v is equal to omega r, that's what we just talked about last time, and therefore omega is equal to the speed over r. You could substitute that in for omega, and there's another way to calculate this, that the centripetal acceleration is equal to the speed squared over r toward the center. Those say the exact same thing. It just depends on whether you know the speed or the angular velocity. Okay, so here's something a little weird. Let's go back to that rolling example we just did. Assume that the speed is constant. What's the centripetal acceleration vector at the top and bottom? Okay, so we saw that at that instant, the point that's in contact with the ground doesn't have any velocity, but it is going to have acceleration because this thing's moving in a circle and its velocity isn't constant. Anytime an object isn't moving with a constant velocity, it has to have acceleration. So, and actually, let's just, since it's moving with a constant speed, let's just calculate the total acceleration. Okay, so at the bottom, the acceleration of the bottom relative to the ground is equal to the acceleration of the bottom relative to the center of the circle plus the acceleration of the center of circle relative to the ground. This one is 0 because the center is moving with a constant velocity. So now let's think about this acceleration of b with respect to the center. That's equal to the tangential acceleration plus the centripetal acceleration. And this is 0 because we have a constant angular velocity. So AC, from the calculation we just did, or the equation I just gave you, is equal to omega squared times r. Omega, what was omega? 33 point. Can someone calculate this? So we got 33.333 squared times 0.3. Okay, so 333.333, that's meters per second squared. And what's the direction? So we're talking about the bottom There's the center. What's the direction of the centripetal acceleration? Yeah, toward the center. And so what is this in vector components? That's right. 0.333. So that point's instantaneously at rest, but it has a big acceleration towards the center. The top is just the same, except so what's the only thing that's going to change when you do it for the point at the top? That's right. The sign is going to change because from the top, pointing towards the center is down. So it would be 0, negative 333. Okay, and then the last thing we need to do is give an expression for the magnitude of the tangential acceleration. So the magnitude of AT is alpha times r. That's the angular acceleration times r. And this is tangent to the circle if it's speeding up, you know the drill with this direction. It's in the same direction as the velocity. And if it's slowing down, it's in, bless you, the opposite direction as velocity. Okay, so any questions about that? So we have these three formulas for the magnitude. Well, I guess we have two for centripetal acceleration. So here's the take-home message. The magnitude of the velocity vector is equal to omega times r. The magnitude of the centripetal acceleration is equal to omega squared times r, which is also equal to the speed squared over r. And the third one is that the magnitude of the tangential acceleration is equal to alpha times r. All you need is the magnitudes. And then you can figure out the directions separately. Okay, let me give you one more problem to work on, and you can work on this until the end of class, and I'll just start by going over this. I guess it would be on Tuesday. Actually, I might not see you guys on Tuesday. I might not see you till Thursday next week. But anyways, so let's say that the angular position function is equal to 10t squared. What's the velocity vector, the centripetal acceleration vector, the tangential acceleration vector, and the total acceleration vector when time is equal to pi over 10 square root? And the radius of this circle is 0.05 meters. Okay? See if you can do that on the board.